This lesson will examine aerodynamic concepts and enhance the ability to recognize and correct undesired aircraft states. This lesson will cover general aerodynamic characteristics such as aircraft certifications and limitations, high and low altitude aerodynamics, high and low altitude aircraft performance, angle of attack, AOA, and stall awareness, stick shaker, other stall warning devices, the stick pusher, Mach effects, airplane stability, control surface fundamentals, the use of trim, icing and contamination effects, and propeller slipstream. The following objectives will be covered during this lesson. Identify aerodynamic concepts and how they can be utilized to prevent or recover from upsets and stalls. Describe the effects of icing and other contamination on aircraft aerodynamics and how those factors may increase the likelihood of an upset or stall. Explain the controls utilized by the flight crew to alter aerodynamic forces for prevention or recovery from upsets and stalls. ICAO and IATA use the same definitions for a stall: an aerodynamic loss of lift caused by exceeding the critical angle of attack, AOA. The definitions also note that a stalled condition can exist at any altitude and airspeed and may be recognized by continuous stall warning activation, accompanied by at least one of the following: buffeting, which could be heavy at times, a lack of pitch and or roll authority, and an inability to arrest the descent rate. Several factors affect stall conditions. A change in weight will not change the AOA at which the wing will stall, as the maximum lift coefficient, CLmax, is fixed for a given wing configuration. However, it does change the speed at which the stall will occur. The load factor for level flight is exactly 1. As load factor increases during turns, turbulence, etc., the effect is the same as temporarily adding weight to the aircraft, and stall speed increases. In a climbing turn, the higher wing, with the greatest rate of turn, has the higher AOA and will stall before the inboard wing. With a descending turn, the lower wing has the highest AOA, and at stall the wing will drop, increasing the bank angle even more. As stall speed is directly related to angle of attack, it remains the same, but the true airspeed, TAS, where the stall occurs, increases with an increase in altitude due to lower air density. Stall speed decreases with engine power applied. There are many fixed devices which delay or otherwise improve stall characteristics, such as winglets, leading edge cuffs, stall fences, and vortex generators. Rime ice, hoarfrost, bugs, and other dirt will cause early boundary layer separation, and stall speed will increase. Aircraft certification and limitations are determined by individual state regulations, though there is broad commonality with ICAO and IATA member states. A stall warning system is required, and many controllability and stall characteristics are mandated. Certification procedures are extensive and may be found in ICAO Annex 8 and FAA AC 25-7D, just as examples. It is important to understand that upset prevention and recovery training, UPRT, requires aircraft OEM participation because aircraft control characteristics are aircraft specific. Although there are significant procedural commonalities between many aircraft, it is entirely possible that a recovery procedure learned for one aircraft assignment will vary from the procedure required for a different aircraft. The high-altitude environment requires pilots to remain attentive and vigilant. Available flight envelope between low and high-speed buffet may be quite limited, and maneuvering-induced loads or external forces, such as wind shear and turbulence, can result in exceeding airspeed limitations or even upset conditions. The area where maximum limiting airspeed approaches stall speed is known as the coffin corner. Use of vertical speed mode in climb can lead to a critical airspeed loss and potentially to a stall. Pilots should be aware of the climb capabilities of their aircraft. Attempting to comply with a restrictive air traffic clearance, such as B level in 2 minutes, may also lead to a critical reduction in airspeed. Vertical speed mode prioritizes vertical speed over airspeed. If a rate of climb which is too high is selected, when the aircraft thrust limit is reached, rate of climb will continue to take priority and speed will decay as the autopilot attempts to maintain climb rate, which may lead to a stall. Airspeeds at or below minimum drag speed should be avoided. Speeds below the indicated minimum drag speed, VIMD, are referred to as being on the backside of the drag curve and are inherently unstable. In this regime, an external force such as turbulence may cause a speed reduction which results in further speed decay if additional thrust is not immediately applied. If not immediately arrested, the speed decay will continue and could result in stall or a need to initiate a descent to regain airspeed. While climbing to level-off altitude, at around 5,000 to 7,000 feet below the planned level-off altitude, the outside air temperature, OAT, should be checked to determine if the temperature is greater than 10 to 14 degrees higher than shown on the weather data, and a request for a lower altitude may be necessary. Optimum altitude is reduced by an increase in OAT. If an increase in temperature is encountered while in level flight, buffet margins will be reduced and a descent may be necessary. Be aware that though an aft CG improves fuel efficiency, it also reduces aircraft pitch stability and increases susceptibility to upsets. When reverting to manual control at high altitude, pilots should be aware of decreased aerodynamic flight control damping due to the density of the air and avoid over-controlling the aircraft, as this could lead to an upset. Bank angles beyond 15 degrees should be avoided, as the additional drag could exceed the thrust available and lead to a speed decay. Conversely, in a confirmed upset or stall situation, full control deflection may be required to regain control of the aircraft. At low altitude, flight control input forces are noticeably different than at high altitudes. Due to aerodynamic damping, at a constant speed it will require greater control deflection at low altitudes to achieve the same rate of change in attitude. This is significant in that approaching stall, control column inputs by the pilot may need to be greater than expected. In a low-altitude upset, achieving an attitude change may require full control input. This is only one reason manual handling training, pitch, power, roll, yaw, should include training on non-intuitive factors. It may be counterintuitive to use greater unloading control forces, possibly to the stops, when recovering from a high AOA, especially at low altitudes. If the aircraft is stalled while already in a nose-down attitude, the pilot still needs to push the nose down, unload, in order to reduce the AOA. Altitude cannot be maintained in a stall and should be of secondary importance. At lower altitudes, the energy state of the aircraft is more kinetic. It comes mostly from the engines propelling aircraft speed. The pilot does not have 6 to 7 vertical miles of potential energy to command. With that vertical distance comes time, a critical resource. This lesson has shown how high and low altitude effects differ regarding aerodynamic performance. Thrust or engine stability and performance differences are also critical to upset recovery, as shown in the AUPRTA resource shown above. Energy is required to recover from slow flight and stalls. However, immediate additional thrust may compound recovery efforts for aircraft with engines mounted below the wings. This problem is magnified by engine acceleration, as the relative wind, angle and volume entering the engines is impossible to judge. The time delay from thrust control input to engine acceleration is therefore unknown, and engines may accelerate at an inopportune time during the recovery, leading to a secondary stall. This is true at any altitude. At lower altitudes in denser air, the fuel control units can mix more fuel and air into the engines given the same amount of time. While this makes the engines a better energy source at low altitude for speed recovery before proper AOA is achieved, it can delay recovery. At high altitudes with such great potential energy, drawing energy from altitude may be a more prudent solution as significant additional thrust may not be immediately available. The AOA which produces the maximum lift coefficient is known as the critical AOA. The critical AOA at a given aircraft configuration is Mach dependent, as the critical AOA at high Mach is lower than at low Mach. Critical AOA increases significantly when slats are extended. Critical AOA decreases when trailing edge devices such as flaps and ailerons are extended. Stalls are always related to high AOA and can occur at any altitude or airspeed. Stall always occurs at critical AOA, but at various airspeeds. As an aircraft approaches stall, it typically becomes less stable, which may cause degraded control surface authority to complete loss of control surface effectiveness. It can also be characterized by reverse control inputs and uncontrolled departure from stable flight in pitch and roll. Prevention exercises, such as approaches to stall ending at the first indication of an impending stall or remaining well below the critical AOA, are not comparable to stall recovery procedures. Safe flight requires an effective instrument crosscheck. The primary flight display, PFD, features enough information to prevent an upset condition and assist the pilot during an upset recovery. Different PFD brands display information in their unique ways, but most have similar sets of information required. For example, all feature an aircraft symbol which displays attitude. A flight path vector, FPV, is a common feature which displays the path of the aircraft. AOA is not the elevation of the aircraft symbol above the horizon, it is the elevation of the aircraft symbol above or below the flight path vector. In the image shown here, AOA is between 13 and 14. Also shown in the image is the pitch limit indicator, PLI, which shows the critical AOA in relation to the aircraft's current AOA as two opposing yellow lines with 3 diagonal feathers each. In the example above, the PLI shows the current AOA is about 1 degree from the critical AOA. The speed indication is shown on the left side of the PFD. In the example above, the aircraft is about 7 knots indicated airspeed, KIAS, below stall speed. The aircraft is traveling below a safe speed turning left and descending with a high AOA. The PFD uses red capital letters to direct the pilot to recover when the flight director, FD, commands them to lower the aircraft nose, which has already started to occur in the example. In this case, at such low airspeed, additional thrust is not needed on most commercial transport aircraft. Further information will be provided in the Uprt class on recognition and in simulator sessions. The AUPRTA app, available for most mobile devices and tablets, can also provide important additional information for further understanding. The AUPRTA website can be bookmarked for similar reference. Both the app and website show PFD and integrated standby flight display ISFD indications of an airspeed indication discrepancy. Pilots should practice active monitoring and regularly perform cross-cockpit checks. As shown previously, some PFDs have a recover warning annunciation. Even PFDs without this option offer speed and AOA information to help prevent pilot-induced stalls. Many PFDs have an AOA indicator option, which allows the pilot to visualize proximity to stall. Where this indication is not available on a PFD, it is sometimes available as an independent indication connected to the AOA vane through the flight computer, much like a stick shaker. Though not a device, aerodynamic buffet is a warning which occurs as the wing approaches a stall. The aircraft design will determine the level of buffeting, ranging from a mild vibration to a prominent pre-stall buffet. An audible warning is provided by an electronic or mechanical device as the aircraft approaches stall speed. The simplest version is a stall warning horn mounted on the airframe, which produces a warning sound when the angle of airflow through it reaches a selected point. A stick shaker is a device which is used to warn the pilot of an imminent stall. It is mounted on the control columns of most civil jet aircraft as shown in the picture above. The warning is indicated by rapidly and noisily vibrating the control column. An avionics computer takes external AOA sensor information from multiple sensors, and when the data indicates an imminent stall, the computer actuates the stick shaker and an audible alert. Another stall warning system which may be connected to the aircraft can offer more information on the actual lift coefficient. A dedicated AOA sensor will provide input to a computer which has predetermined AOA calculated for each possible configuration. The system may have an AOA indicator which offers a visual indication of the aircraft's proximity to the critical AOA. A stick pusher is a device some fixed-wing aircraft have to help prevent an aerodynamic stall. and is also referred to as a stick nudger. A stick pusher may be installed as an option on some stick shaker systems. The stick pusher was created for aircraft that are susceptible to deep stalls, and they are seen most often on aircraft designed with T-tails. Stick pushers were designed to prevent a pilot from allowing an aircraft to enter a stall. The stick shaker is an awareness tool, while the stick pusher is a prevention tool. In all cases, stick shakers will activate before stick pushers. In discussing AOA, it has been shown how the critical AOA changes with the Mach number. Next, the effect of Mach on G loading will be shown. Any change of G loading, such as in a normal, level turn, changes the stall speed. Critical AOA will therefore be achieved at lower or higher airspeeds than at 1G. Bank angle alone does not change the speed at which critical AOA occurs. However, bank angle combined with a level or climbing flight path does increase that speed. While in cruise with maximum flight efficiency, the buffet margin is approximately 30% over stall speed. If the aircraft enters a 30-degree banked turn, airspeed would need to be increased by 8% to maintain the safety margin. Since this is not a standard procedure, it is important to understand when flying at high altitude, pilots are strongly encouraged to decrease bank angles for turns, the same way the autopilot operates. If 15 degrees of bank were used instead, the loss of buffet margin protection equates to only 1.4%, which is barely above negligible. Combine these G-loading facts with the effects of Mach number on critical AOA, and it is easy to understand the significance of the cumulative effects at high altitudes. Before finishing with the topic of Mach effects and G-loading, here are some additional points to understand. The previous slide showed the effects of G-loading on the critical AOA in normal cruise flight. Shown here is how G-loading is used to improve the speed at which the critical AOA occurs. If G-loading is reduced to less than 1G, but greater than 0G during stall recovery, a pilot can significantly decrease stall speed while keeping passengers in their seats and flight attendants off the ceiling. As shown in the chart above, if a pilot uses 1/2 G, stall speed decreases by 30%. If 1/4 G is used, the decrease is 50%. Critical Mach number occurs when airflow over a wing reaches Mach 1.0, causing a shock wave to form over the wing and Mach buffet to occur. As speed increases, Mach buffet increases as the shock wave moves aft, moving the center of pressure aft as well. This causes a nose-down tendency, which has been termed Mach tuck. Static stability is the initial tendency of an aircraft to return to an undisturbed state after a disturbance. Static longitudinal stability implies all the forces and moments around an aircraft's CG at a fixed flight condition and attitude are balanced or in equilibrium. Static stability is dependent on 3 factors: location of the wing with respect to the CG, location of the horizontal tail surfaces with respect to the CG, and area of the tail surfaces. It is determined by the relationship of the CG and the center of pressure, also known as the center of lift. There are 3 designations for static stability. Positive static stability is the initial tendency of an aircraft to return to its original state of equilibrium after being disturbed. Neutral static stability is the initial tendency of an aircraft to remain in the new condition after its equilibrium has been disturbed. Finally, negative static stability is the initial tendency of an aircraft to continue away from the original state of equilibrium after being disturbed. An aircraft's intended purpose will dictate its performance design. Stability is assessed and control is designed from the performance design. Training aircraft require docile handling and are very stable. Fighter jets today demand extreme maneuverability in a wide speed range and an unstable design, which requires computer control augmentation. Dynamic stability is how an aircraft responds to a disturbance over time regarding whether the aircraft will return to equilibrium, how long it will take to return to equilibrium, and what may result if it does not return to equilibrium. The diagram above shows the 3 types of dynamic stability. Positive dynamic stability has an aircraft returning to equilibrium over time by way of decaying oscillations. If the amplitude of a disturbance does not decay over time without external inputs, such as a pilot, the condition is said to have neutral dynamic stability. If oscillations are divergent over time, or amplitude increases in severity, the aircraft has negative dynamic stability. The most common design feature used to produce directional stability about the aircraft vertical axis is the vertical stabilizer, acting like a weather vane and providing a steadying influence. The most common feature designed for roll or lateral stability is dihedral, which raises wingtips upward above the wing roots. This is true whether wings are basically straight or if they are swept. Current technology designs use swept wings for efficiency at high speeds. However, there is a cost to stability. To explain the effect by example, if an aircraft is disturbed by a lateral wind gust, it will first push the tail opposite the direction of the gust, causing the downwind wing to push forward and the upwind wing to swing back, creating more lift on the downwind wing. Greater lift on one side will create a rolling moment. As the downwind wing rises, it also slows down, decreasing lift. This occurs while the upwind wing descends and goes faster. The greater the lateral component of relative airflow on the descending wing, the more lift is created on that wing, resulting in a rolling moment which opposes the initial disturbance. The cyclic nature of the yawing and rolling oscillations is referred to as Dutch roll. On older swept-wing aircraft, Dutch roll was a significant problem which could cause structural damage and hull loss. Although unlikely, yaw damper failure and/or certain autopilot failures could cause disturbances which may initiate Dutch roll, even on today's advanced aircraft designs. At low airspeeds, controls feel soft and sluggish. The aircraft reacts slowly to control inputs. At higher speeds, controls are increasingly firm and aircraft response is more expeditious. Design features limit flight control surface deflection and control stop mechanisms may be built into flight control linkages. Limiting available movement of control columns and rudders may also be used. These design limits help prevent a pilot from inadvertently over-controlling and over-stressing the aircraft during normal maneuvering. Shown here are secondary flight controls. There are 5 common types of trailing edge flaps. All extend the camber of the wing for greater lift and slower flight. Some also increase the wing area. It is important to note that flap extension may cause a nose-up or nose-down pitching moment. The type of aircraft will determine the kind of compensation required by the pilot. Slots direct air over upper surfaces of wings during high AOA and lower stall speed, providing control during slow flight, but they are not designed into transport category aircraft. Slats allow higher AOA and decreased stall speed and are available on many commercial transport aircraft. Leading edge flaps increase the maximum coefficient of lift and the camber of the wing, allowing greater control at low airspeeds. Leading edge cuffs also increase the maximum lift coefficient and camber, but are fixed devices, so there is a cruise penalty. Trim tabs and balance tabs reduce the force required to move primary control surfaces. Anti-balance tabs increase the effectiveness and feel of primary control surfaces. Servo tabs assist in providing force for moving a primary flight control surface. Finally, spoilers decrease lift and can augment aileron control. An autopilot which works properly is an excellent tool for flight. Some events and autopilot system irregularities can cause a large-scale out-of-trim condition commanded by the autopilot. It is very important to have firm control on the control yoke when disconnecting the autopilot for any type of upset. Excessive use of manual pitch trim may aggravate an upset or result in exceeding a structural load limit. If needed, trim should be used sparingly. The effects of icing on performance include decreased climb rate, decreased cruise speed, decreased service ceiling, decreased range, decreased missed approach performance, increased fuel consumption, and increased stall speed. Tests conducted on many modern airfoils by NASA's Glenn Research Center demonstrated that the biggest degradation of performance usually occurs within the first few minutes of ice accrual. In some cases, exposure to clear icing for 2 minutes could increase drag by 100%, reduce lift by 25 to 30%, and reduce critical AOA by 8 degrees, a substantial amount which increases stall speed dramatically. NASA has demonstrated how critical AOA can increase 8 degrees within 2 minutes. Leading edge and upper wing surface icing can increase stall speed by up to 15 knots. Wing ice can also disrupt airflow over ailerons. An aileron may deflect without pilot input and cause an uncommanded roll. Due to design, CG is most often forward of the center of lift. The horizontal stabilizer counteracts the resulting nose-down pitch with downward lift. To prevent a tail stall, the airflow must stay attached to the lower surface of the tail. Ice-contaminated tail stalls are almost always associated with extended flaps. As flaps are lowered, wing downwash increases, which increases horizontal stabilizer AOA. Increasing speed and thrust can also increase horizontal stabilizer AOA. Ice on the tail increases AOA and can disrupt airflow under the stabilizer, making the elevator less effective. The elevator may oscillate without pilot input and cause an uncommanded pitch change. In extreme cases, the control column may snap forward, immediately pitching the nose down. Pilots should be aware of the insidious nature of icing and contamination effects. Inaccurate information from unreliable airspeed sources, failures of stall and ice alerting devices, and degradation of flight envelope protection systems may not be obvious without a disciplined flight deck scanning technique. The first audible indication a pilot may receive could be whaler activation when the autopilot disconnects due to pitot-static system icing, as seen on Air France 447. This image should be recognized from the AUPRTA resource. A propeller converts rotational motion into thrust. Like other wings, the dynamics of the blades are based on Bernoulli's principle and Newton's third law. The magnitude and effect of the spiraling slipstream varies greatly between aircraft designs. There are no easy rules of thumb which can be provided to isolate these forces from other propeller phenomena. Rotating air changes the direction of the local airflow at the side of the fuselage and vertical stabilizer, causing a yawing motion to the left for clockwise propeller rotation. This phenomenon varies with aircraft design, power setting, AOA, and airspeed, both in effect and magnitude. Yawing moments produced by propellers are mainly caused by the spiraling slipstream, depending on the aircraft, but for conventional configurations, approximately half of the yaw is caused by the slipstream striking the fuselage aft of the CG. The other half is from this slipstream striking the vertical stabilizer. Wind tunnel research indicates that approximately 6/7 of the total yawing moment is produced by the spiraling slipstream, and the rest comes from P-factor or asymmetrical thrust. Spiraling slipstream occurs constantly, however, and has greater influence over the airflow at slow speeds and high power settings. The rudder is used to counteract these effects, which results in less rudder control authority to the right. This must be taken into consideration for any upset recovery procedure. In summary, this lesson identified aerodynamic concepts for use in recognizing and recovering from upsets, stalls, and other undesired aircraft states. This lesson described the characteristics which influence the aerodynamics of an aircraft, including design, configuration, contamination of flight control surfaces, and other factors. The way these factors influence the critical AOA, or the speed at which a stall will occur, were also shown.